Hi guys. Okay, so in this video, we are going to cover the PowerPoint presentation on Chapter 1, Essential Ideas, from section 1.1 to 1.3, which relates to the matter. So this is a brief introduction of the matter. We will look at the various phases and the classification of matter, physical and the chemical properties of the matter. We know that everything all around us is made up of matter, not only on this earth, but also outside the earth in the cosmos as well. So we will look at the historical development of chemistry. Like chemistry is a study of matter, but how did this discipline evolve? So we will look at the examples of chemistry as it relates to our daily life. We'll look at the scientific method, differentiation between the hypothesis, theories, and laws. And then we're going to look at the examples that illustrate the macroscopic, microscopic, and the symbolic domains. So first of all, chemistry is a study of the composition, properties, and the interactions of matter, and attempts to understand the behavior of matter. They relate to more than 2,500 years ago. In the past, we had developed a method of understanding the matter, and that method was basically alchemy. In other words, it was a very crude way of trying to understand matter, in which every rock or anything that was of interest was dumped into fire, and then it was melted. And then once we got the molten matter, we further extracted and we tried to determine what was this particular substance made up of. So this was a very old method that was used, not very scientific, but at least the beginning of chemistry. Chemistry as a subject is not only a subject which operates by itself, because everything around us is made up of matter. So chemistry is also interrelated to other disciplines. Or in other words, in order to understand chemistry, we need to get information from other knowledge bases also. So for example, we need to know, math, the application of math is in chemistry to understand, the various phenomena. Physics lends its knowledge to chemistry, so we can make sense of, why the atoms or the molecules or why the matter behaves in a certain way. Okay, then nowadays computer science is evolving, where we are using simulations or cheminformatics to simulate artificial molecules using the artificial intelligence, and we are trying to determine the behavior, the properties of these new molecules. So that's again making use of the computer science or artificial intelligence. Then there is a discipline called chemical physics. There is nanotechnology or nanoscience at a very small scale. Material science, all kinds of matter is made up of a variety of different things. So material science is one of them. Chemical engineering, there's biochemistry, there's environmental science, agricultural, food, biology, medicine, toxicology, geology, right? Geochemistry, nuclear chemistry, all of them are all related to chemistry. So chemistry, is a central science. Okay, we see chemistry in our daily life happening all around us, starting with ourselves first. The food that we are digesting in our body, that metabolism, that is a chemical process. The clothing that we wear is coming from the textile industry, that is a chemical process. The plastic cookware, the food items that we have in the kitchen, the containers, right? All those, or even the steel, all those are coming from the processes where chemistry was applied. Even the plastic on the credit cards is, made from the chemicals, which were obviously manufactured in the plants. Then the gasoline that we see in the cars, right? That is coming from the crude petroleum, and it is refined in the refineries, and finally it comes to us, and we are able to. So there is a mechanical energy, there's a chemical energy, all these are involved. Next is many different examples of changes in the composition and structures of matter, that leads to the formation of new and new compounds. So we see that the matter can change, matter can change physically, matter can change chemically. Okay, physical changes are the temporary changes, but the chemical changes are the permanent changes. And then there is change in energy that accompanies the changes in matter. So all these are tied together. Now, in order to understand science or basically chemistry, we have to start with some kind of observation, right? You see that when you keep a piece of bread on the table, after some time, the mold grows on the bread and the bread goes bad. You take a piece of iron, you put it on the table, that piece of iron begins to rust. When the piece of iron is rusting, that is a chemical change happening. So sometimes, when you make these observations, then you see, consistently, is this happening or is it something that is happening once in a while? So you begin to develop some kind of, hypothesis or a guess is that, okay, every time I leave this iron rod outside in my yard, it begins to rust. But when I take that iron rod, I bring it at home and I wrap it up like in a cloth or something, and I put it inside my, like a drawer, then it doesn't rust. So these are the things, you observe and you say, okay, why does this happen? So you begin to develop a hypothesis. Now, what is hypothesis? Hypothesis is just a tentative explanation of the observation. In other words, it is an educated guess. Okay, so these educated guesses are basically based on all this information that you may have from these different disciplines. This could be happening because of XYZ information or some phenomena that you have known or learned in some other discipline. So basically, you just relate all those concepts, okay? Next is you decide. Then once you decide, okay, this could be happening because of that, so that's your hypothesis. Then you design an experiment. When you design an experiment, that experiment needs apparatus. Then that experiment needs, you need to take the data. You need to formulate the data in the tables, and then you see the data. You see the patterns in the data. Do you consistently get the same results? You introduced variables. Okay, variables are you keep one variable stationary and the other one you move. Okay, every time at this temperature, do you see the same thing happening or not? You change the temperature, do you still see the same thing happening? You increase or decrease the temperature, and then you see what results do you get, or what observations do you get? You note down your observations, then you see the relationships in these data points. And usually sometimes there is an outlier. This data is presented in a form of tables. You can collect them, and then you can make charts, you can make graphs, and then you can see, how these data points connect with each other. Do they increase with the increase or decrease? And is it a linear relationship? Is it a positive or a negative slope? So you make those graphs, and in the graphs, you see which ones are the outliers. And why are they the outlier? Why is there an outlier in the data? It's not that you made a mistake, maybe you did, but the data is data, and you did the experiment, you follow all the steps, and then someone else, when they repeat those same steps, do they get the same results? So those things, if the experiment is not repeatable by another person, then you need to figure that thing out. Why? And if the people are able to repeat that same experiment and they're getting the same results, the same pattern, then it becomes sort of a rule. And if it's consistently done in all these more variations, then it becomes a law. So you will see the laws. There are many laws in science. There are Boyle's law, Charles' law, Gay-Lussac law, all these gas laws, right? Avogadro's law, Dalton's law, right? And then there are other laws like the laws in thermochemistry, thermodynamics, right? The first law of thermodynamics, second law of thermodynamics, and many more, right? So all these laws, then you combine together and becomes a theory. A theory is a well-substantiated, comprehensive, testable explanation of particular nature. So like, it's your body of knowledge, basically. Now, there are three types of domains in chemistry. One is a macroscopic, the other is microscopic, and the third is the symbolic domain. Macroscopic domain is something very big and large, which you just see with your open eyes, just normal things you see all around you. Microscope is it at a microscopic level. You cannot see it with your naked eye, but you need some kind of apparatus to see it, like a telescope to see the stars far away, or a microscope to see the cells. And now we are able to see the atoms also, right? So those microscopic domains are very, very small. And sometimes you just have to imply them. Sometimes you have to you trust them that they exist. And that's the difficult part of chemistry. That's where the real chemistry happens. Okay. Then the symbolic domain is where we have a language of chemistry actually. So we are trying to express the behaviors of the molecules. We're trying to express that phenomena in a very condensed symbolic domain. So we don't like to write big words, letters and all those things, like long sentences. So we just express things in symbols. Just like you have symbols in math and symbols in physics, same symbols are there in chemistry also. So this is a pictorial representation of the scientific method. You start with the observation, and it comes through either a curiosity or also serendipity also leads you there. But in any case, it's always the observation. You form an educated guess. Why is this happening? So in other words, you have to think. Now think about it. Newton saw the apple fall. Everybody saw the apple fall. It's not just Newton alone who saw the apple fall from, and he came up with his laws of physics. It's not that. Everyone saw the apple. It's been happening all the time. But Newton was the one who began to think, why did the apple fall? What is happening here, right? So here's the thing with this thing that, when you think, then you come up with some, more logical explanation to that phenomena that you're observing. Okay, so you form a hypothesis, which is an educated guess, and then you have to look for, even in that hypothesis, to support that hypothesis, you have to look at the theory from other disciplines. Okay, then you perform an experiment. Okay, when you perform an experiment, do you see consistently the same results? Then yeah, that proves your hypothesis, that's correct. Yes, the results are consistent, okay, with the predictions, and it contributes to the body of knowledge. Okay, then this becomes your, then it kind of becomes, then it becomes like a rule or a law. But if it's not, then your further testing is required. So you go and further, either you refine your hypothesis, or you change the experiment, or you change the apparatus, you make or you change the variables, or you do those things. And once this keeps looping, until and finally you reach to some kind of conclusions. Either the hypothesis becomes the theory, or your observations become a law, but an additional testing or additional work is needed. And that's how the science has evolved. Chemistry has evolved, particularly. One experiment led to another experiment, and then it's a huge body. And that's how we learned about matter. Okay, now this big picture shows you microscopic, macroscopic, and the symbolic domains. So macroscopic picture is the big one. We see water, we see ice, and then we see the clouds, or we see the air. That's macroscopic, big picture. What is this made up of? That is the microscopic domain. So you see, this whole big thing is macroscopic. Microscopic is this. In microscopic, okay, this is made up of molecules. And what molecules are there? The water molecules. And water molecules are H2O, 2 atoms of hydrogen, 1 atom of oxygen. All this information we come through the microscopic domain. So this is where the real chemistry is. 2 atoms of hydrogen, 1 atom of oxygen, bonded, but at an angle. You see that? They are arranged at an angle. So this information is all coming from the microscopic domain. Now comes the symbolic domain. What is a symbolic domain? Symbolic domain is these symbols. 2 atoms of hydrogen is H2, and 1 atom of oxygen is O, so H2O. H2O, that is the way we write water. Okay. Next is other symbolic domain is the phases, the gas phase, the solid phase, the liquid phase. Now, S stands for solid, G stands for gas, and the L stands for the liquid. Okay, next is, just give me 1 second. Okay. Next is, we see that this solid is in the solid, the molecules of water are arranged in a very definite pattern. They are spaced out, yes, but they are arranged in a very, very definite, arrangement. So that is the situation with the solids. Liquids, the arrangement is more haphazard, in other words, more fluid. The particles are close to each other in both the cases. However, here they're in a random order. So that is why they move, they flow. But in gases, the particles are very far away. The molecules of water are very far away. So that, that tells us that the gases, there is less attraction in the particles. Solids, there is the most attraction. That is why they're arranged in this pattern. And liquids, there is kind of minimum attraction. They're still close, attracted to each other, but they are, still not arranged in an order. Okay. So the three states of matter, solid, liquid, and gases, as we have seen. Now we're going to look at what is it that differentiates the mass and the weight. So matter, as we know, is anything that is mass and weight. So it has mass and volume. So we will look at that. Next is, what is the law of conservation of matter? We'll classify matter, and then we will look at the examples of atoms and molecules. So we talked about matter. Matter is anything that has mass and occupies space. The three states of matter, solid, liquid, and gases. Solids, definite shape. Liquids take the shape of the container. Gases also, like it's an indefinite shape. They may take the shape of the container. The volume also is indefinite for the gases, because gases love to expand. Gases love to contract. I mean, they don't love to contract, sorry, but they love freedom. They can, expand. So that is why their volume is not very definite. Okay. Then comes the way we show them here, the three common states. This is like, very definite shape. They take the shape of the container. Here they spread out, but if you remove this, they will spread out more, okay? Expands as it takes. So that's the deal with the gases. But there's also one state of matter, which is called plasma. And if you take the gas, so here's another thing. You take solid, you heat it, it melts, it becomes a liquid. You take liquid, you heat it, it becomes a gas. You take gas, you heat it, that's when it becomes plasma. Okay, plasma is a state of, electrically charged particles. Okay, now plasma is found in stars, in lightning, and it's also found in the television screens. Okay, so its properties are very unique, and they're not like the gases, but somewhat like liquid and gas, like it flows. Plasma also flows. So that's the deal with the plasma. Now here's another thing. Solid, if you take solid and you freeze it, then it becomes Bose-Einstein condensate. In Bose-Einstein condensate, the matter begins to lose its identity. Okay, so hydrogen and the oxygen, they all look one. They don't look different. Okay, so that's the deal with Bose-Einstein condensate. So anyway, so here's a plasma torch. And plasma, it's such a high temperature, and this is a metal, right? So what is this plasma doing? Such a high temperature, and that like it's used to cut the metal. So it's used, in these type of applications. Okay, next is, what is a difference between mass and weight? Mass is a measurement on the amount of matter that is present in the object. In other words, like the particles, how many molecules, how many atoms together, combined together, make that substance. That is the mass. Weight, on the other hand, applies to the gravity that exerts on the object. So the weight can vary, the mass cannot. Mass relates to the number of particles that are actually making that substance. That particles could be atoms, could be molecules. But the weight, on the other hand, how much of the gravity is pulling on that particular object, that can vary. Something that has a certain mass on this earth will have a different type of mass number, the weight on the moon, and on Mars it will be totally different. So you see, it all depends upon the pull of the gravity. So less gravity on moon, lighter the object is. Substances that are heavier on this earth are going to float in the outer space, because less gravity, okay? An object's mass is the same on the Earth and the moon, but its weight is different, as we looked at that. All right, next is law of conservation of matter. What does this mean? This means that you cannot destroy the matter. Matter is always going to be transformed from one form to another. When you apply a change on a matter, that change can be a physical change or a chemical change, but that change can lead to a conversion or transformation of the matter. Like, for example, you take salt, which is solid, right? You dissolve in the water and it vanishes. But what has actually happened is it has solubilized, or it has become soluble in the water. So that look of that has changed, right? And it's just that but the amount of salt that was added in water, and that doesn't change. So in other words, when you do a chemical reaction also, in a chemical reaction, whatever reactants you start with, you produce the exact same type of products. The mass remains the same. The total weight on the reactants and the products remain the same. Like, for example, here, whatever ingredients you put in before, sugar and like whatever, to make the beer or the alcohol, if you seal it, it's not going anywhere. It just stays inside and it just transformed. A new substance is formed. Here you take the sheets of lead, you take lead oxide, and then you take sulfuric acid, and then they just rearrange atoms and molecules. They just rearrange. A new substance is formed, lead sulfate and water. But the amount of weight of lead oxide and sulfuric acid and the weight of lead sulfate and water, that remains the same. That doesn't change, okay? Next is the element. What are elements? Elements are the type of pure substances that cannot be broken down into simpler substance by chemical changes. In other words, elements are made up of only one type of particles, and those particles are called atoms, okay? There are 100 types of known elements in the periodic table. The rest of them have been synthesized. So this is the reason why the elements also get very particular names. Like, for example, the one that got synthesized in Berkeley gets the name berkelium. The one that got synthesized in Livermore gets the name livermorium. You see that? So those things. So no, those there are about 90 of them are naturally occurring, and then the rest have been, like I said, synthesized in the laboratories, nuclear labs. Okay, next is what are pure substances, and then what are mixtures. The pure substances are made up of only one type of particles. Those particles could be atoms, those particles could be molecules. Two types of pure substances, elements and compounds. Elements are made up of only one type of particles, atoms, and they cannot be broken down into simpler substance by chemical changes. Compounds, on the other hand, can be broken down into some simpler substances by chemical changes, because compounds are made up of two or more types of particles. As you see in this example, gold made up of only one type of particles called gold atoms. Phosphorus made up of only one type of particles called the phosphorus atoms. Oxygen, just oxygen by itself, not in a combined state, but oxygen, only one type of atoms, oxygen atoms. Same is the case if you take, you've all seen copper in nature, like, at home, copper wires. Aluminum foil, made up of only one type of atoms called the aluminum atom. Silver, same story, okay? So these are only one type. So that is why when you apply some chemical change, nothing new is going to be formed, because they are all made up of only one type of particles. On the other hand, on the compounds, they are made up of two or more type of particles. So it's, yes, you can break them. Look at hydrogen. Look at oxygen. So you can break this by passing an electrical current. This is sugar. You can break the sugar. You can heat it up and it can convert to carbon dioxide and water, and then you can further break up carbon dioxide and water also. Silver chloride, you can break up silver and chloride. Silver chloride, silver and chlorine can be separated by chemical means. But like water, because water is made up of only one type of molecules, H2O. Sugar is made up of only one type of molecules, C6H12O6. Silver chloride made up of only one type of molecules, AgCl. So they are here is another interesting thing, that water, hydrogen is highly flammable. Oxygen is also highly flammable, but when they fuse together, they produce water, which is inflammable. You see that? So the properties of the molecules is totally different from the properties of the atoms that make the molecules. Carbon is dark black in color. Hydrogen itself is a gas. Oxygen is a gas. But what is sugar? White granular sugar, white colored, solid on top of that, right? So you can see it. You can actually like eat it. Obviously, we eat it every day. So sugar is basically made up of these three atoms, and each of the atoms have a very different property than the actual sugar. Okay, so that's the compounds and molecules. Now, so let's say, for example, here, a mercury and oxygen, when they combine, when mercury and oxygen are heated together, so mercury has a different color, oxygen is obviously colorless, but when they mix together, they produce this red colored mercuric oxide. Okay, so we see this is the mercury is liquid. On the other hand, mercury is liquid, gas, oxygen is a gas, but when these two combine together, they produce solid mercuric oxide. Okay. And then similarly, when you heat them, then again, you can decompose the mercuric oxide. When you take mercuric oxide, it's going to decompose and give away oxygen, and it leaves the liquid mercury behind. So that's, so that's the thing with the chemical reactions. Next comes the pure substances and mixtures. What are pure substances? Pure substances made up of only one type of particles. As we said, could be atoms, could be molecules, but mixtures. Mixtures are mixtures, as we said, they are made up of two or more substances, and that's why they're called mixtures. But the mixtures are just like it's not a chemical reaction, it's a physical change, and they can be removed by the physical process. Okay, so a mixture is composed of two or more types of matter that can be present in varying amounts and can be separated by physical changes. Now let's look at, first of all, two types of mixtures: the homogeneous mixture and the heterogeneous mixture. Homogeneous, homo means one, they look one, but heterogeneous, you can see the individual constituents. Homogeneous, for example, here is the Gatorade. Here we have some salts, right? They were mixed in water and they produced this nice one clear solution. This clear solution, fine, it has red color, it doesn't matter, but we cannot see the individual components here, right? So that is homogeneous, means look the same. Like, for example, if you take sugar and you take salt, you mix them together, it will be one thing. It will look like one mixture. On the other hand, here you have the wine or vinegar and you added oil to it. So oil and water or vinegar, they don't mix. Oil and vinegar don't mix, or oil and wine don't mix. So here is this wine, and here the water oil droplets floating on the top. Okay, so here's the thing, that in this case, this is a heterogeneous mixture. Okay, so matter does, so here's the thing, how do we determine whether something is a pure substance or a mixture? Does it have a constant properties and composition? Does it look like the same properties, same composition? If it is yes, then it's a pure substance. If it is a pure substance, can it be simplified chemically? If it can be simplified chemically, then it's a compound. But if it cannot be further simplified, cannot be broken up into different atoms, then it's an element. Okay. On the other hand, if the mixture does not have the constant properties and if a matter does not have constant properties and composition, that means it's matter. Is it uniform throughout? Then it's homogeneous. If it is not, then it's heterogeneous. So these are the, from time to time, we in chemistry, we see these concept maps, which relate all these different concepts. And, these are called the flow charts, or these are also called the mind maps. So I highly encourage you to make these mind maps, these for your own personal understanding or learning. How are they connected? How are these things connected? How all these connect? Because chemistry would be very scattered. Another thing about chemistry is what you study in chapter 1, 2, and 3, you are going to apply the same thing in chapter like 5, 6, 7, 8, 9, and even further. So it's very spread out. So in order to connect all these loose ends or these concepts, we make these concept maps. Okay. So I encourage you to do that. It helps you to visualize the whatever you learn. Okay. So anyways, what is an atom? An atom is the smallest particle of an element. It has got properties, and it has a certain, chemical and the physical properties. Okay. Next is Democritus and Lysippus. They were the first people who said that, okay, they were great philosophers, and everything could be made up of the smallest particles that has the physical and the chemical properties, and that substance is called atom. And then Dalton further came up with this idea, and see, everything, that is why I'm saying in chemistry we need math, and this math is used to to further validate our conclusions or our understanding of the matter. So quantitative measurements were used, and different experiments were also done to prove the structure of matter. So John Dalton came up with a proper structure of matter. Okay. Molecules consisting of 2 or more atoms connected by the strong forces, and these strong forces are called chemical bonds. Now we have now an advanced technique, the scan tunneling microscope, the STM, that can generate views of the surface of the solids, such as the image of the gold crystals. So here, for example, is a gold crystal, as you would see from your naked eye, the golden nugget. But if you put it in the microscope, the scanning tunneling microscope, this is how the gold looks like. And these small, round pieces, these are the atoms. So we have now, seen that yes, every substance is made up of atoms. It has been proved, now through the technology also. But we do have many other experiments which actually came up with the structure of matter. And here's another thing, you are going to study further that the structure of atom, that there is a nucleus, and then there are energy levels, and actually these energy levels were using light, using light to understand actually not understanding the energy levels, but also quantifying them, right? So we will study that in quantum mechanics, but for now, let's just keep this very basic, that atom. So this is cotton, right? Cotton, macroscopic level, bigger, we just see it as a white ball. But if you take the cotton strand and see it under the microscope, you would see it is made up of this. Under the scan tunneling microscope, you would see something looking like this. And even further at the microscopic level, we can see how these atoms and the molecules are arranged. Even further, we can see that these atoms and molecules are arranged in a certain patterns, in certain angles, in a certain like arrangement, that molecule that gives that certain properties to the to that particular substance. Okay. So we will be doing molecular modeling, or this is just to show you that the atoms of hydrogens connected like this, oxygens connected like this, phosphorus, sulfur, all these. And then these are the molecules made up of 2 or more. So these are just the atoms, pure atoms, elements that would be, but these guys, when they combine in different, combinations, and again, these combinations or the bonding in the molecule is also very definite. It's a very definite ratio. Like, for example, carbon can combine with 1 atom of oxygen and give you carbon monoxide, but carbon can combine with 2 atoms of oxygen and give you carbon dioxide. Both of them have very different, unique properties. So once again, these are just these more pictures on the macroscopic, microscopic. Now let's look at the physical and the chemical changes, or the properties. First of all, physical properties are what you see from outside. Physical properties are such as, the color of a substance, whether a substance is hard, right? The hardness, the softness, the color, the taste of a substance, the smell of a substance. okay? Whether it is a solid, liquid, or a gas, right? Then we look at the melting points, we look at the boiling points, we better see whether it's a good conductor of electricity or not, whether that substance can be made into thin sheets or not, whether you can make it into wires, whether you can, what is the density of the substance? Is it going to float on water or will it sink in water? So these are all physical properties, okay, that just basically which describe the substance as it looks. On the other hand, the chemical properties. The chemical properties of a substance are based on how is it going to react? Is it going to catch fire or not? Is it, causing toxicity? Will it, kill something? Is it fetal? Then acidic, will it corrode? How is it going to react with other things, with other substances? Will it produce heat or will it need heat? All these are the chemical properties of a substance, okay? So for example, here you see this butter. So physical change and chemical change we will look at in a minute, but this is again, you see this iron, when it combines with oxygen, causes rust. But on the other hand, we have chromium. It does not react with oxygen. Steel does not react with oxygen. Gold does not react with oxygen. Silver, also for the most part will not. Okay, so that's the chemical nature, the chemical property of a substance. And here we have like the physical properties: gold, soft, yellow colored, like that thing, this is an iron or a steel. You can tell when you look at substances, when you touch them, just by their physical means. Now, chemical nature of a substance, like for example, these are the bananas, rotting bananas or rotting food. That's the chemical change happening. The food that you're cooking in the kitchen, this is the meat. It goes through some kind of a chemical reaction when you're cooking food. When you're burning things, burning incense, or this candle or a matchstick burning is a chemical change. Here you take copper wire. Copper wire is brown in color. You mix it in with what is it, nitric acid, which is the HNO3, is transparent, clear. But when the two mix, what does it produce? A blue colored solution. And this blue colored solution is a new substance is formed, which is copper nitrate. And the brown colored gas that is liberated is nitrogen dioxide. A new substance is always formed whenever a chemical change takes place. And in a chemical change, you cannot revert back to the original substances, the starting materials. In other words, your rotting banana cannot go back to the original banana by just ordinary means. The food that you cook now cannot go back into the same, chicken you made, the chicken that you used, the raw chicken that you used. Impossible, right? Same is the story with where once something got burned, the carbon dioxide and water have left in the, they are in the environment. You cannot convert them back into this matchstick. Same thing in this reaction, so we cannot. So chemical reactions are like permanent changes, but physical are not. Then there are two types of properties, extensive and intensive. Extensive properties, this depends on the amount of matter present. Amount, how much, what is the weight of the substance? That weight determines, how much it is going to weigh on this earth, the mass, the volume, the space that is going to occupy, or the amount of heat it is going to absorb. Okay, these are the extensive properties. Intensive properties are the ones that do not depend on the amount of matter. Density does not depend on the amount of matter. The boiling point, the temperature, of a substance is the temperature at, once it gets hot, that is the intensive property of a substance. Okay. Now we all know that the elements have been arranged in a certain order. And that order is represented in the periodic table. But before we go here, I want to cover a little bit more, which is not here, but physical change and chemical change. A physical change. A physical change is a change in which the property of the matter that is being mixed, that does not change, but it's only temporary change. So physical change is, you can recover the individual components in a physical change. Like, for example, salt and water mixed together. Okay, salt is solid white and water is liquid, transparent. When they two mix together, the salt vanishes and we say, oh, it's gone, you know, and we may see a nice clear solution. And just looking at it, we may not even know that the salt is there. But when you taste it, yeah, you would say the salt is there. But how do you recover the salt back? You evaporate it. So evaporation is a physical process, okay? Now, next, say you have mixed alcohol and water. Now, alcohol and water look the same solution. And it's only when you touch or smell, it's only when you smell it or you taste it, then you know that water contains alcohol. But let's say you want to change, you want to separate the water and the alcohol. Then what do? You take a distillation flask, you put the two things together, the water and the alcohol begin to boil at a certain temperature, right? Both of them will boil at a different temperature. Let's say alcohol boils at 40 degrees Celsius, roughly, I'm just assuming, and water boils at 100 degrees Celsius. So the thing that boils first is going to convert into water vapors through the distillation flask, you know, those vapors pass and then they condense and they're collected on the other side of the distillation apparatus. And then you separate the water and the alcohol by the differences in their boiling points. So first methanol or the alcohol boils off and it's collected as a vapors, and these vapors are further condensed. And then comes the water boiling off at 100 degrees Celsius. So that is, distillation is also a physical change. Okay. So now last piece we are doing today is this arrangement of the elements in the periodic table. And now I am going to show you the actual periodic table, which is, just 1 minute. Okay. All right, so let's look at now the periodic table. And here is our periodic table. All right, so what do we see here in the periodic table? The elements. First of all, every element has a symbol. So you need to memorize the symbols of the elements, okay? And I have another video in which I have explained that the names or the symbols of these elements, there is a certain, you know, pattern to it, which you can apply to learn and, you know, go from there. But here is just a general introduction that the metals are those substances. We find more metals in the nature. Metals are those substances that are solid except mercury. They have very high boiling points, very high melting points. They are shiny, you know, in different degrees. They are also, you know, good conductors of electricity and heat, and they can be made into thin sheets. That is, they are malleable. They can be made into wire. That is, they are ductile. So that's the properties of the metals. These metals have a place in the periodic table, mostly, you know, left-hand side and in the middle and a little bit on the right-hand side. So the ones that are in the first column, they are called the alkali metals. The ones that are present in second column are the alkaline earth metals. Then comes the elements that are in this 13th. So these are a mixture. So this is a non-metalloid, but the rest of them are called a post-transition. The middle ones are the transition elements. The middle ones, the transition metals. Post-transitions are on the right-hand side in columns, you know, 3A, 4A, 5A, and 6A. And they are the post-transition at the bottom left side. Next comes on the bottom side of the right-hand side, sorry. Then comes the reactive non-metals, the non-metals that form the bulk of the compounds or the molecules we see in the periodic table. Then comes the noble gases, okay, which do not react. with general, but we can force them to react, by changing the chemical, by changing the conditions, okay? So every element has a number, which is the atomic number, okay? Then another number right here is the mass number. That is the weight of the atom. This is the number of, this number on top represents the number of protons. So if there is one proton, that proton determines the identity of the atom. One proton is only going to be hydrogen. But if there are two protons, it's going to be helium. If there are three protons, it will be lithium. 4 protons will be beryllium. 5 protons is boron. 6. And what are protons? When we study the structure of atom, then we will delve into it more. But right now, you just keep this in mind that the protons are present in the nucleus, which gives the number of protons are the ones that give the identity to the atom. So 6 protons will be carbon, nothing more, nothing less, a dark black colored solid carbon. But if you add one more proton, it becomes nitrogen, vanishes in the air, we can't even see it. One more proton to the nucleus of an atom, it would be oxygen or life force. One more proton in the nucleus of the atom, it becomes, with 9 proton, it becomes fluorine, which is very toxic. Then comes 10 protons in the nucleus, and that is neon, which is non-reactive, and that is a gas. And one more proton, that is with the 11 protons, solid, sodium, very reactive. You see that? So we see that these, as the number of protons change, the identity of the atom also changes. When with that, the properties also change, okay? So we see here that every element has a symbol and then the name also. So you have to memorize that, okay? So with that said, this finishes the introduction to the matter and the first part. And then there are other videos also, which I highly recommend that you should see. But for now, we are going to stop here, okay? Thank you. Bye-bye.